Let me record this. So,
Okay.
worksheet, GD&T worksheet number 2 today. This is the 4:15 morning class. As far as the assignments that you're being given today, looks to me like it's just more questions to be answered. 8:13 through 8:24. So, no drawing projects. The quiz, of course, is at your discretion as to when you want to finish that up. This is the PowerPoint, which again, like Mondays, is not very involved. Basically, it just says, hey, we're going to work, we're going to use the GD&T worksheet number 2. We're going to use this website. If we want to review anything from Monday, we're open. I'm open for that. We can do that first. We can do it later or in the middle. I don't really care too much. So here's worksheet number 2, and again, we're using the GD&T website from Engineering Essentials to answer these questions. This is the link. We're going to talk about perpendicularity. Question 1 says that perpendicularity recognizes that the two surfaces will not be perfectly perpendicular. What does the tolerance zone look like? So if you're going to draw the tolerance zone for perpendicularity, you're probably just going to do something like this. I mean, if you do it in a 3-dimensional form, it'd be great, because in effect it is a 3-dimensional tolerance zone. It does have length, width, and depth. So you know, this for your own benefit. If you draw it out, it just maybe will kind of reinforce understanding what it looks like. But otherwise, the tolerance zone, if you draw it and make it look like this, that's fine. The thing about perpendicularity is we're relating two surfaces, or at the very, theoretically, a surface on a plane, and that plane happens to be 90 degrees from the surface, or should be, or vice versa. Maybe the surface should be 90 degrees from that plane. But, in reality, we don't have, we can't create that plane, so we have to use another surface. So generally speaking, perpendicularity always involves two surfaces: our datum control surface and our datum reference surface, and then our controlled surface, which would be the surface that we're actually putting the tolerance on. So let's see where they show it here. The control surface and the datum surface. I thought there was a better shot of it, but so we have the datum feature here, which is and then we have the control surface, which is here. The control surface will have the feature control frame pointing to it or attached somehow. And this is what the feature control frame looks like. We're pointing to this surface and saying that it has to be perpendicular within 0.1 to another surface. And it could be this surface, if that's, if that's datum surface A. If this were datum surface B and we wanted it to be perpendicular to that, well, then we could add B to it, or we could just use B. So we could use both, or one or the other. If you have more than one surface that's a datum surface, but generally don't, because if this is a datum surface and that's a datum surface, they're kind of in conflict. So
in this case, it would really relate to the function of the part, or you'd have that. In this case, they're telling us the back of the part or the bottom of the part. But like you said, if you had it up at that top piece up there, that little step, then
Right.
maybe the part would actually relate to that surface instead of the other surface.
That's true. If this were an important surface, this were a mating surface, for example, then we'd probably want the datum feature symbol up on this surface. And then we would want to relate, assuming that this is also probably a mating surface. So yeah, you have to look at the way that they check this stuff. To get an idea of what we're looking at. And I'm kind of, again, I'm not a real big fan of this particular setup, just because looking at our part, this is our datum feature, the bottom of the part. So that's laying on top of the, it's sitting on the surface plate. And then they're using a gauge block here, bumped up against it, and a gauge wire, kind of like a no go, to check to see if this thing falls within the limits of the tolerance. The problem I have with this is that this surface back here, not on the gauge block, but on the part, this surface here could be perfect. If you look at the top and the side, from here to here, it could be perfect, but it could have a bow in it like this.
Yep, exactly.
Right? And when you bump it up against this gauge block, the edges are going to be in contact, and so this gauge wire won't go in, and you should be, so you should be good. But in reality, they could have a big depression in the middle of that surface, and that's not, that probably is not the design intent, and really it does render that surface to be not perpendicular to the datum surface. So I kind of like this one better because
in general practice as an inspector, that's how I would check that part.
Yeah.
The second drawing here.
Because the second one.
You're right, because otherwise you can't control whether there's a divot in the middle of that.
No,
face.
But here you can. Here you can see it with the dial indicator. Yeah, that's why I prefer also. Because now the datum surface is clamped to the gauge block, and now we're checking the control surface. And if there's a divot, dip in there or anything like that, we're going to see it with the dial indicator. And if it falls outside the tolerance zone, then we know it's a bad part. So to go back to the questions, what does the tolerance zone look like? We already talked about that. Why is it necessary to call out a datum in the feature control frame for perpendicularity? Because you need to have a reference surface to establish perpendicularity. We can't use a theoretical plane because you can't create that. And then it says draw a feature control frame to control perpendicularity to datum A within 0.25. So again, if you look at the feature control frame, it would look just like this, perpendicular to 0.25, and the datum reference would be A. So it's perpendicular to A within a tolerance of 0.25. So pretty easy. And parallelism, 4, 5, and 6. Pretty much well, let's look at perpendicularity of an axis first. Even though there's no questions on it, let's just take a quick look at it. When I look at this, I think, I can't use straightness of this axis or cylindricity of this thing as a gauge as to whether or not this part's made correctly, because what I'm looking at here is a cylinder that's got a straight axis, and it looks like it's probably theoretically cylindrical, perfectly cylindrical, but the axis itself isn't perpendicular to this surface right here. So if this were indeed a pin or a bolt of whatever it might be that we're trying to insert in this hole, if the perpendicularity isn't controlled, then this is what's going to happen. So other than the fact that they are, that this is cylindrical and this is a flat, or a block, the perpendicularity feature control frame and the tolerances that you set up are exactly the same as you would for that other example. The only difference is that because we are dealing with a diameter, or whether it's a hole or a solid cylinder, when we create the feature control frame, we have to make sure we put a diameter symbol in there. Mm-hmm. And that's because the tolerance zone is going to be a cylinder. It's going to be round, and it's going to have basically 3 dimensions, right? It's not length, width, and depth, but it's the diameter, which basically controls X and Y, regardless of where you're at, and then the length of the cylinder itself, or the depth of the cylinder. So because the tolerance zone is circular or cylindrical, you have to make sure you add a diameter to the tolerance, because we want to make sure that whoever's looking at this understands that that tolerance zone is circular or cylindrical. It's not just a distance between a couple of planes, right? We don't see that here. We don't see those planes like we see in perpendicularity of a surface, right? We see the 2 planes that create the tolerance zone, right? But for perpendicularity of an axis, it's a cylinder. So that should be fairly, fairly easy to comprehend, I guess, based on what we saw in the last slide. I don't know. Is this how they check it? Yeah, maybe not. I don't know. I guess if this is the surface that we're trying to control, then we would want to check it this way, because if we were to say clamp this thing, well, I don't know if this is round. So if it's not round, then yeah, we'd want to have our datum surface on some sort of a surface plate or piece of ground, flat ground material that we can put this through, and then put a dial indicator on this and rotate this or whatever we got to do to check that, to make sure it's perpendicular. However they do it, you know what I mean?
Or in today's world, we'll use a CMM to do that.
Yeah, exactly. Right. Yeah, this thing preclude. I don't think it assumes that everybody's got a CMM either.
Right.
So
and well, the other thing too is you can't run every time to the measuring machine to check everything as an operator. So you have to have a means to check it at your station.
Right. And if you're doing piece parts, then you probably got some kind of a fixture.
Gauge type,
yeah, you got a fixture or jig to check that stuff with. So back to the worksheet then. Let's look at parallelism. So the question here is which part has sides that are perfectly parallel? Well, yeah, it's the same question and answer every time. Right. So in the case of this particular part that they're showing us, they're only concerned with these 2 surfaces, the outside surfaces. They haven't created a relationship between the 2 inner surfaces. So they're showing again a datum plane or surface, and then also a control surface that has the tolerance zone in it. And again, it's a 3 dimensional tolerance zone. We're not just looking at line contact. We're not running or measuring from here to here in a couple of spots and saying, oh yeah, it's within the tolerance for being parallel. So in this case, we're measuring this whole thing against this whole datum surface to make sure that it falls within. So again, it could have a bow in it, and we, depending on how they check it, we'd want to find that, because that might preclude it from being parallel. Here's what the tolerance zone looks like. Here's what the feature control frame looks like.
Right.
The parallelism symbol. Again, the tolerance then, and then the datum reference or the datum surface that we're measuring from to determine whether or not we fall within the tolerance for parallelism. And again, you place the feature control frame on the surface that you're controlling, obviously, and you've got a datum feature symbol on your datum surface or feature. In this case, they are they've got a tolerance, the dimension for the length between, or the distance between here and here. And it would seem that if you have this, would you need to have a parallelism GD&T feature control on that? You know what I mean? If you're measuring, I don't know if it's just coincidence that they happen to be the same, how they set that up. Let's read what it says here. It says to apply a parallelism control, the FCF, the feature control frame, may point to the surface or be attached to the extension line that extends it. So shown below applies a parallelism tolerance to the entire surface. So the entire surface must lie between two parallel planes that are 1.1 millimeter apart. They don't mention the fact that they've also got the linear measurement between these two surfaces at the same tolerance.
But then again, if I was trying to check that with a micrometer, I'd check the corners and they still might miss the middle and have a divot in it. That's why they've got it set up down on the bottom there with the
exactly.
dial indicator.
I'm not disagreeing with that. I'm actually looking for an answer from you guys as to why did we need to control it? Go ahead.
Yeah, I would think that probably it's a little overkill myself, but engineers.
It could be, but again, it might not be, because regardless of how this feature is, I mean, this feature could have a depression in it and still fall within this tolerance for parallelism to this surface. And at the same time, if this part fits within an accurate say a distance between two other parts, you still would have to control the overall length, regardless of what this does for you for that surface. You still probably need to. So, like you said, maybe your corners are perfect and within this, but your center isn't. But those corners could be, they still have to conform to this tolerance as well.
Right.
So there's no reason why. I think it's just coincidence that they happen to have 10.1 to 10, and then have a parallelism tolerance of 0.1. I don't think they always have to. You wouldn't always have to match these two. And if you were going to tolerance this distance from the datum surface to the control surface, it doesn't necessarily have to be the same tolerance for that distance as it is for the parallelism tolerance zone. that could be different. It just depends on the form, you know, and the function of that part. Yeah, and I tend to agree that, you know, this is probably a decent way to check that, because if you zero, I mean, without even knowing what this is, this distance, if you just zero this dial indicator somewhere and then start moving it around, you know, if the dial goes, you know, beyond 0.1 in any direction, either direction, you're you know, you're going to be outside the tolerance, and you don't need to know what this dimension is in order to check that. So that's why I say they're, you know, they're independent of each other.
Right. The other thing though is you could actually check both at the same time by using Joe blocks and set the gauge up to the right height.
But we're not
But we're not worried about that.
Right. We're not worried about that in this class. Take the metrology class to argue that with that instructor.
No, I'm not arguing about it. I was just saying that, that you could.
Yeah,
you know.
Yeah, I got it. So going back to the worksheet. We know what the tolerance zone looks like. It's a set of parallel planes. You can draw it, you know. You could do a partial of this thing and show the tolerance zone. I'd be happy with that. You wouldn't need to draw this whole gizmo here. Again, why is it necessary to call out the datum, a datum in the feature control frame? Because you have to have a reference surface to create a parallelism tolerance. Can't be parallel to thin air. And then when you draw do the feature control frame, you're going to do it just like it's shown here, except it's datum B, and it says to within 0.1, yeah, 0.15 right here. So pretty self-explanatory. Okay. Position of an axis. That video that I had put the link up out to and put on the outline is pretty good at explaining it. Says position recognizes that a cylindrical feature won't be located at its true location or position. What does the tolerance zone look like for the position of an axis? So let's go take a look at position of an axis. So again, we're talking about a cylindrical tolerance zone. So if you were to just draw a circle with a tolerance zone in it, and then, you know, or, you know, the end view of a cylinder, and then draw a cylinder with, you know, with a tolerance zone like that, I'd be happy with that. Just so we have an idea. You don't have to put all this stuff in here. We already know that whenever you're putting position tolerance on a location, that you're going to be using basic dimensions to locate it, which are theoretically exact numbers, and then using the tolerance in the feature control frame to control the actual location of that variance that's allowable off of the perfect location. So that's why it's necessary to use basic dimensions to locate the true position, because the basic dimensions will locate the exact perfect point for that feature, and then the tolerance in the feature control frame will tell you how much it's going to vary. So I guess a second reason why, or a second way of looking at it, would be if we didn't have these shown as basic dimensions, then the fact that they were whole numbers would automatically put a tolerance on the location or the variance of this dimension and this dimension, right? Because if we have nothing else, telling us what that location is, then this would revert back to maybe the tolerance block and the title block. So now you'd have some conflict. You'd have the tolerance of the unboxed dimension based on the tolerance block And then you'd also have a position location feature control frame, probably giving you a tighter tolerance than what the tolerance block's giving you on these. So in order to eliminate any other outside factor, that's another reason why these need to be basic dimensions, so that there's no other tolerances that are trying to impinge on our setup here, and create some conflict. Why is it necessary to use multiple datums to control position? And it says, hint, use the figure at the bottom of this page to help answer the question. What they really mean is the figure at the bottom of the web page.
Right.
So let's look at the feature control frame, first of all. The first panel is going to be the symbol, which is the target, crosshairs, however you wish to describe it. The second panel is going to be the tolerance itself. And again, because the tolerance zone is cylindrical, we need to add a diameter symbol to that number, whatever it is. Now, when you do this in SolidWorks, SolidWorks doesn't know that what particular surface you're going to put this feature control frame on, so it doesn't automatically add this diameter symbol. So you have to add that when you create the feature control frame, and I'll show you that after we're done with this on our P311 project. And then you have, after the tolerance, you add the panels for the datums that you're referencing. Almost always 3 datums, I think, for any type of for a hole for sure, and I would say probably for anytime you're doing a cylindrical feature, whether it's a hole or a cylinder, a solid cylinder, you're going to have to use 3 datums. We looked at this guy, and then to answer this question about why is it necessary to use the multiple datums, when we look at how, not so much how this is checked, but yes and no, I guess, in terms of how it's checked, but you might think that we would only need to reference B and C, right? Because when you look at these features, we've got a cylinder and a hole, a solid cylinder and a hole. We can locate them both from C and from B, right? So why do we need all 3 datums? Why do we need A? What do you think? Let's say we had this part up in the air like it is here, and if this is C and B, that means we would push, this would be our datum check feature or surface B, and this would be our check feature C. So if I push this thing up against these 2,
well, if I've got it sitting there and sitting in the air like it is in that first left-hand corner there of the below,
yeah, right here.
Yeah, that can still tilt left or right, even though you've got it butted up in there. It still could be not flat.
It could tilt this way, is the way
exactly.
I look at it.
Yeah,
and that's going to throw off your dimensions.
Right. It'll move the center of those points.
Right. Exactly. That's exactly the reason why you need the 3 datums, because when we look at this tolerance zone, it runs all the way through the part, doesn't it?
Right.
So yeah. So if I were to datum here and here and not worry about datuming on the back side of it, for example, or the front side of it, whichever one happens to be my 3rd datum, when I could check this hole, and even in a feature like this, a fixture like this, If depending on what I'm doing, if I've got a pin that's, that if I stick a pin in here, and let's say I only stick it in so far, and I take a measurement back to this surface, and it all looks good from here to here. If that hole is actually drilled or bored or whatever at an angle, it may look good on the surface here, but when I get down to the bottom, it could be at a different location that's out of round, or out of tolerance.
Right.
It's kind of like drilling a hole. When you drill a hole, and you got you can see it more with a fairly small drill bit. How many times have you drilled a hole and it's come out? You're even doing it with a drill press, and you can see the drill bit flex, right, from the forces that are created when you're trying to cut that hole. It's going to push every time that cutter comes around. It gets turned in the hole to try to cut away material. There's a reaction that's going to try to push back on it, and that's going to tend to flex the drill bit. So I don't know about you, but I've drilled many holes where I thought I was drilling them perfectly straight, and when I look at the other side after it breaks through, it's not. It's not straight. Yeah, it's oblong. It's oblong down that end or whatever. Right.
There's a rule of thumb that an engineer at Sunstrand told me a long time ago, that the drill is going to be off. It's going to deviate off its center by 2 times the diameter of the drill over the depth.
2 times the diameter?
Yep, 2 times the diameter of the drill. I said, oh, really? And
it
seems excessive, but
yeah, it seems excessive.
And I think it might depend upon the size of the drill too. But
it's for sure.
But
if you got an 1/8 inch diameter drill bit and you're cranking it, you're not watching your how fast your speed and feed. That's quite possible. It's quite possible, and it still wouldn't break the drill bit probably.
No, it wouldn't.
But that seems. But anyway, that's the reason why, because you don't want to, you don't want to create another, add another factor in there that might affect how well this is checked. Like I said, I mean, if somebody's just saying, well, hey, I'm going to put a pin in here and measure from here to to the end of that side of that pin and subtract half the diameter, and it comes in both ways just fine, well, that's great. But they haven't, if they haven't really, if the pin doesn't go all the way down, then or they got a plug or something like that that has a shoulder on it, so that it only goes in a certain depth. They don't know for sure what the other end of that hole looks like. So to get back to the question, that's why the reason why we want to use multiple datums to control the position is so that we know that we're checking we'll be checking or helping to assure that the location of the hole from where it was started and where it finishes up are all going to be within that tolerance zone, because that is a cylindrical tolerance zone, and that's why we want to use those 3 datums.
Right.
So we can control the 3 directions that tolerance zone actually exists. So I can't think of an easier way to explain that. I mean, to me, the best thing is just looking at the fact that if this part were to tilt in the fixture, the way they've got it shown here, that would throw off the location. So we want to make sure that it's located properly in all 3 directions. So draw a feature control frame to control position within a diameter of 0.5. Again, just happens to be right there. So really all you do is copy that. Make sure you put the diameter symbol in there and you should be good. Right?
Right.
So no problem.
Then we could throw things into a real quandary by putting maximum material condition on it.
Yes, exactly. And I don't know that we really want to talk about maximum material. But maximum material will, of course, for a hole is the smallest that the hole can be.
Mm-hmm.
So when you're looking at this tolerance zone now, when the hole enlarges, it actually gives you a kind of a whatever that outside tolerance of the hole is, kind of gives you, at least material condition, gives you a bonus tolerance, because
Right.
now, even though you're limited at maximum material, you're only limited to here. And if that would bring whatever's fitting inside here, this right here, now, if we go to least material condition, then that increases our tolerance zone for the location.
Right.
It actually gives you, whatever, a bonus of whatever that difference is between the maximum and the minimum, or the least.
Mm-hmm.
Yeah. So, but again, that's really a subject that's probably more correct for the metrology course. We're just trying to give you a basic idea of what GD&T is all about. And like I said, you can devote an entire semester to a GD&T without much of a problem. So, any questions on any of these questions?
No, I'm good.
The Department of Redundancy Department is asking if you have any questions on the questions. Mike, you're good?
Yeah.
Okay. All right. Let's move on to SolidWorks. This is our part, our P311 part. I took a few things off of it from Monday, but I left our datums. So we've got datum A, and I left our flatness control. So we've got datum A, datum B, and datum C, which is the front of the part. And I left the extra C on there. So we have I think, I don't recall exactly, but I'm only going to demonstrate how to put some feature control frames on. I'm not going to do them necessarily on specific or correct surfaces for the project, for the drawing project, because I don't know off the top of my head what they are. I think one of them is parallel to B, so I'm assuming it's this surface here. So let's start with that. We want to put a feature control frame on this surface that says that it's parallel to, or maybe it's perpendicular to A.
Perpendicular to A. That side's perpendicular to A, and then the other end is supposed to be parallel, I think.
Parallel to this?
Yeah.
Okay.
So like where the 1.5 inch side
right
of your
here.
leg, that's supposed to be parallel to B.
Parallel to B.
Yeah.
And is B supposed to be perpendicular to A?
Yeah.
Okay. Well, I don't know and I don't know what the numbers are, but, well, regardless, doesn't matter. So we want to add, this is parallel to B, right? This one is parallel to B.
Right.
Okay, so let's start with that. On the annotations tab, here's our datum feature command for these guys, and above it is the geotolerance command. And it works basically the same as, for this one, it's going to work the same as when we did the flatness. Put the symbol in. In this case, we only had flatness and then the tolerance. For parallelism, we're going to have to add the datums also.
Right.
So we go to our symbol for parallelism, which is these two lines right here, the angled parallel lines.
Right.
Whatever the tolerance is, I don't know what it is offhand. I'm going to pick 0.005.
10 thousandths. 0.010.
All right. 0.010. Do I need a diameter symbol in here?
No.
No, I don't need a
Flat
right.
surfaces.
Yeah.
Flat surfaces.
Right. 2 flat surfaces. And then I have to choose my my datum surface.
Right.
I only need one datum surface here because I'm going to say that A is parallel to B.
Right.
So the primary datum is not going to be A though. It's going to be, and you see it doesn't show up in here. And none of that stuff shows up in here.
You have to type it in.
Yeah, you have to type it in. So my primary datum is going to be B.
Right.
And this is what my symbol looks like now. If I just say OK, well, here's what happens. It just throws this thing out here somewhere, wherever it was, and I can't do anything with it. Other, I can't. It's not like when I did this guy. Before I closed it out, I actually attached it. So if you forget to attach it, this is what you wind up with, and you can't attach it to any surface. If I let's see if I can modify it from here. Doesn't look like I can, but if I double click it, I can. And what does that give me? Does that give me the opportunity to put a? Doesn't give me the opportunity to do anything with it. So it seems like I'm stuck, and the only thing I can do is if I do highlight it. So if I highlight it without double clicking it to modify it, if I just highlight it and I get the property manager here, I can go down here to leaders and say, hey, I want to add a leader to this guy. So when I do that, now it's got a leader, and if I grab this point, I can attach that point to the surface or this surface, or try to get the whole, because of this radius. What I'm trying to do, the reason I'm playing with it is because I want to make sure if I drag it off here that I'm going to get a gap. And I'll show you what I mean. If I put it here, now it's attached to that surface. Okay, see that?
Right.
But if I drag it out here, it may or may not show a gap. And you see it doesn't show a gap.
Right.
It might be because of the fact that it's a radius here. If I drag it down here, however, then it does show a gap. And the reason for that is because I attached it close to the closer to this end of the part of the surface toward the bottom. If I try to move it up here to this surface, can I make it or not? Now you can see that because it's close to this end, there's no gap. But if I drag it up here, now it's showing a gap. That's the reason why I was playing around with it. So that I could show you the difference between, or the difference that where you place the leader makes in terms of showing this gap. So now we got that parallel to B. And then B should be perpendicular to A.
Yes.
Within, I don't know what.
5 thousandths.
Okay, so let's go back to geotolerance. Again, I'm working on it. If I do this, now I've just basically placed an empty box in there. And if I hit escape, this is what I got. So here's the way most of us, I think, do this. I want to say it's going to be perpendicular. There's my perpendicular symbol. tolerance 0.005, and my primary datum again is going to be A. So there's what the box looks like, right? The feature control frame. So now before I do anything else, I want to move this guy if I need to, if he's covering up the area that I want to, the surface that I want to control. And then I'm going to drag this thing over here and place it on this surface. Like so. I wanted to actually, and then I can hit escape or hit OK, and I should be good. But now I want to drag this guy off. But when I do, even though I'm close here, closer, I'm not getting a gap. And that's, again, because of this radius, I think. So if I were to take this and move it out to here, now I get a gap. So now, you know, I could have also moved it down here, but when I do that, now I don't have a gap. I've lost the gap that I had because I'm covering it up. So you just have to be kind of mindful where you place that the leader based on what you want to do with it. And then we have the perpendicularity to A. Mm-hmm. Right? B is perpendicular to A, and this surface is parallel to B.
Right.
So what does that do for this surface and A?
Well, it's going to make them perpendicular, basically.
Yeah, but the tolerance is going to be
bigger.
Bigger. It's going to be a combination of the two.
Right.
Right?
Yep.
So, you know, that's another thing to keep in mind. If you want this to be, you know, if you're thinking you need to have parallelism to this within a certain tolerance, and then also perpendicularity to this within a certain tolerance, then you could add a perpendicularity tolerance to this, but you'd have to make sure that you understand that they can't conflict. I can't, if this is 5 thousandths perpendicular within 5 thousandths to A, and you've got this parallelism tolerance to B, you can't say that I want this to be, you know, perpendicular to A within 1,000th of an inch, because you'll never achieve it based on the tolerances that you've got here that are going to stack up. You can't achieve that. So you have to make sure that you understand what you're doing. Maybe you don't want, maybe instead of doing this, you just want to create another perpendicularity tolerance between this surface and A. You know, and then if it falls, if you make it 0.005, well now, you know, you're going to probably fall within this to begin with, based on where this one winds up and where this one winds up in terms of perpendicularity. You'll wind up with this anyway. So sometimes that's a better, you know, it just depends on the application. But it's something to think about. You know, you can over define the part with this stuff, just like you can with dimensions. So again, now I don't know if this hole is the one that's got the position tolerance.
Yes.
It is. Okay. Well, let me go ahead and put a couple dimensions on it. And let's call that basic. And then we'll put a dimension from, and I chose this because it's C, right? And then I have to dimension it from here to here because that's datum A.
Right, and you need to make that basic as well.
Make that basic also. Mm-hmm. So now we're going to look at a position tolerance for this guy. Again, fairly easy. The only thing you have to think about is what the tolerance is going to be And also I need to add a diameter symbol before I put any tolerance in there. Well, fortunately, they include most of the common symbols that you're going to need up here. You don't have to search for anything. So the first thing I'm going to add is diameter. And then let's see how this works out. I don't know what the tolerance is. Let's call it 0.01.
Yeah, it was 10. It was 10 thousandths. Yeah.
Oh,
and
okay.
Yep. And then
So
maximum material
yeah,
conditions.
And you see, it's also maximum material condition.
Yep.
So I add then the circled M for maximum material at the end. Diameter symbol to begin with, the tolerance, and then the maximum material. That all went into this single panel. I don't have to add a second tolerance, but I could if I wanted. So my primary is going to be the same as whatever my primary dimensions, right, are set up. And A is always the primary, B is always a secondary, and C is always a tertiary. So I just basically go, hey, primary is A, right, fill in A there, click over to this one, B is secondary, and C is tertiary.
Right.
And there's what my control frame looks like. Attach it to the hole. And I'm good.
Yep.
But let me show you something else though. So now we also have to call out the diameter of this hole, correct? And right. I don't know what that dimension is, but I'm just going to go ahead and put whatever this comes out to be. It probably has a tolerance on it, but I'm not going to worry about that. I'll let you guys figure that out. Well, now I've got 2 leaders coming off that hole, and I don't necessarily like that. If I go ahead and grab this guy to the point where you see it highlights, now they're both highlighted. Let's see what happens. When I let go of the left mouse button, it took away the leader and it basically merged these 2 together. Even though they're highlighting separately, if I drag this around now, they are both attached to the same leader. And that's a lot cleaner looking than having the 2 leaders. Wouldn't you say?
Oh yeah.
Can I separate it? I don't know if I can separate it or not once I do that. Maybe I've never bothered with it, but if I add a leader here, what did it do for me? Not much. I said, yeah, I want a leader here. It's still attached. So I'm not sure if there's a way to detach that and put a leader back on it, but I don't know why you would want to. This is a lot nicer. It becomes part of the whole call out, the diameter call out, and kind of cleans it up a little bit. Any questions on that?
No.
No.
I believe that that's all we have. And we still managed to take up about an hour. No questions on any of the homework assignments? Any issues with filling out any of the tables? The fit tables for the ANSI or metric?
I think I got it. I hope I got it.
Same. I was going to say ANSI was just more annoying than anything.
It is, isn't it?
Yeah.
Yeah, because of the conversion you have to do with the numbers. Yeah, that's true. And I said that, when we first covered it, that it just seems like somebody just didn't want to type all that stuff out when they first made the tables. I don't know. I'm not sure what the logic was behind it, but there must have been some kind of logic, whatever it was. All right, I'm going to stop the recording now. I'll probably use this recording to post. I didn't post one from Monday, but the gist of everything is pretty much the same. So